All right. So next Thursday is our test of chapter 6 and 7. I know time's flying. It's like there's only about just over like 6 weeks left of class. So we did chapter 6 last week. Most part was pretty decent. We're gonna look at chapter 7 this week. Chapter 7 is not too bad. It's more information than and leading us into chapter 8, where we're going to actually be doing a lot more of the calculations and stuff. So, we started talking about the bell curve and figuring out how to do the standard deviation and the mean and how that all worked and how that spread worked. And what we want to be able to do is, because you're never going to be able to look at the entire population. So we want to be able to take a decent enough sample to be able to understand what's going on in the whole population. So we've talked before about how like they do the surveys and stuff like that, and they ask 1,000, 2,000 people what's going on, and then they take that information and they project it out to the entire population. So how do they actually do that? And how many people do you actually have to interview to get a good estimation of what's going on? So that's what we're going to start looking at today, is how they actually start to come up with some of those numbers. So the IRS publishes individual figures every year. This obviously is old data because of the book. So for the year 2010, the IRS reported the mean tax individual income returns was $11,266. So technically, the IRS has all the data, so it could look at the population. However, computer time and everything else to verify things makes it a little bit harder. So what they actually do is they report a sample of it. So they go through and they randomly select a group of them and they do the sample. So they looked at 308,946 tax returns out of the 130 million that they actually got. So, and that was their mean. Question is, well, how close is that to the actual mean of all the tax returns? So let's look at a few things first. What's the population that they're considering? So what's the population that we're looking at here? So remember back to the very beginning when we start to look at definitions. Population is not necessarily a number, it's what the data is representing. So what are we looking at here? Yeah, so the population is all the individual tax returns. Okay. And the sample was 308,000 of those tax returns. What's the variable that I'm looking at? So what piece of that population am I looking at? Because there's a lot of data on the individual tax returns. If you ever did your taxes, like there's a lot of information on that. So what's the variable? What's the piece of information that I'm looking at on those tax returns? Yeah, how much money you get back, right? The return. All right. So whenever we're looking at data, that's the first couple things we want to start looking at, because that's what you're going to represent. So what's the population? What am I talking about? What's the variable that I'm looking at within that population? Because the population could have a lot of variables in there. We could be looking at the number of dependents claimed. We could be looking at the adjusted gross income. We could be looking at the number of deductions. We could be looking at a lot of things in the individual tax returns. So when you're representing it, when you're talking about it, you have to specifically state what piece of what variable or information you're talking about. Now, that $11,266, is that a sample mean or the population mean? That's a sample mean. So that's the other thing. It's like making sure we understand what pieces we're talking about. All right. If they wanted the population mean, they would have had to give you the mean of all 130 million tax returns. Is the mean of the 308,946 the exact same as the mean of all 130 million? Why? Okay. Could it be the same?
They could fit into each other.
They could be the same. Be lucky. It could be close. It might not be exact. All right, but that's not necessarily the exact mean. If we took a different set of 308,000 tax returns, we might get a slightly different mean. So if I'm pulling out this information, we have what's known as a sampling error. So that sampling error is going to give us that range of values that's going to be basically my standard deviation. Right? That's what we were talking about before. It's like we know it's within this range of values. The goal is to try to minimize that as much as possible. All right, so let's look at some stuff. Now, if I was going to do this for this problem here, to actually do all the information, I'd have to come up with all 308,000 things and how many different ways that I could do that out of 130 million possible tax returns. And we can start to see really quickly how that would be an insane amount of calculations that we're going to have to do. So we're going to look at an example that's really simple. All right. That only has a few different variables that we're going to look at and a few different values. It's not going to be realistic. But the goal is to get you to understand what's going on so that when we start to use a computer and stuff like that to be able to do the calculations for larger ones, you understand what's going on behind the scenes on how this actually is done. All right. Yeah, that's what I just talked about. So we're going to take the height of starting players. So when you're playing basketball, it's March Madness. One UConn team's in, one UConn team's not. Fortunately, unusually, it's the opposite of what's normally happens at this time of year. So we've got 5 players. What's the mean height of those 5 players? How would I find it?
Oh,
Add them all up and divide. Good. Find me my mean. Good. So that number is going to be important for a lot. We're going to use these numbers quite a bit today, and that number is going to be used quite often. Keep that number somewhere. All right, that was simple, right? Now, is that the population mean or the sample mean? Did you do all the players?
Yes, we did all the players, so it's
Then it's the population mean. Okay. And so,
I was gonna say, sorry that interrupted you.
That's
I was
okay.
gonna say that in the problem it stated the word population, so therefore
Yeah.
it is the population.
Yeah. So, and that's why I said this is not going to be necessarily a realistic problem because we're going to do a whole bunch of work to try to find sample means now, and I can find the population mean real easy, right? So that's why I said we have to stretch our belief a little bit of this problem. So we have our population mean for this one, but I want to understand how we define sample means and how that varies. So the first thing we're going to do is we're going to do sample sizes of 2. Okay. So we've got the A through E, or what was it? A through E, right? Yep, A through E. So I want to come up with sample sizes of 2. So let's do A and B, A and C, A and D, AE, and then BC, BD, BE, and then CD, CE, and then DE. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different groupings of 2. Does that make sense? All right, so we've got 10 different samples that I can choose from. All right, so now I want you to find the mean of every one of those. So write these 10 down, and then I'm going to switch back to the actual numbers so you can see them. And then how would I find the mean of those 2 numbers? I would just add them up and divide by 2. So that's what you're going to do for each of these. Everybody got these down? Okay, there's your numbers. Sorry, I'm going to make it bigger again for you. There you go. So in essence, what you're doing while doing this is you're doing what the IRS was doing with their 380,000. You're finding the sample. Okay. They just did it with a lot more numbers than you're doing it with. All right, so there's my numbers. What do we notice about these? Well, I think the players are kind of in order. So yeah, so it's slowly, the way they've designed it is it kind of increases based on because of the way the players are, the way they listed them. If they listed them just randomly, that wouldn't have made much of a difference. So we've come up with all the different possible samples that I can have, right? Okay. And the example with the IRS, they just chose one sample, right? They did one sample of 380,000 returns. So if I was to pick one sample out of this, if you were just to randomly pick one, would that be a good representation of the team? Okay. What's the chances that you'd be within 1 inch of the actual mean? What is it? We can figure this out. We have them all. What's the chances that I'd be within 1 inch? So the mean was what? The actual mean was 80. Okay. So we're looking at anything from 79 to 81, correct? So how many are between 79 and 81? 3. So, and there was 10 total, right? So there's a 30% chance that I'd be within 1 inch of the actual mean. That's not great. What's the chances that it'd be within 2 inches? So now we're looking from 78 to 82.
7 or 70.
So we got what? 1, 2, 3, 4, 5, 6. I think it's 7. 1, 2, 3, 4, 5, 6. So 6 out of 10, right? So now we're at 60%. Okay. So this is just a little dot plot of it, so you can start to see the spread. Okay. Does that make sense on what we did there? All right. We're going to increase. Now, instead of doing 2, we're going to do 4. So we're going to do the exact same thing, except we're going to do groups of 4. So we have A, B, C, D. A, B, C, E. A, B, D, E. A, C, D, E. And I think that's it. There's only 5 of them in this one. Yeah. All right. So find me the means of these. Oh, hold on. Let me go back to the numbers for you. There you go. So this time we're going to add up the 4 numbers and divide by 4. Again, I understand this was not as most realistic. It's like, okay, I've added 4, might as well just add the 5. But we're trying to understand process here. If I was giving you hundreds of them, you'd be here forever just adding things up. All right, so if we look at this one, We have 78.50, 79.75, 80.25, 80.50, and 81. So now how many are within 1 inch of the actual mean? 4 out of 5, right? So 80%. So we went from 30% within 1 inch to 80% within 1 inch of the actual mean. So what you're trying to understand is that the more you sample, the larger your sample, the closer to the actual mean you get. Now, realistically, would that make sense? Yeah, it's like the more you do, the closer you're going to get, right? And in this case, we're doing 4 out of the 5, so we should be pretty close. So if we look at this, this is the spread. So if we just took sample sizes of 1, there's 2 within 1 inch. If we took sample sizes of 2, there was 3 within that 1 inch. Sample sizes of 3, 1, 2, 3, 4, 5. 4 we just did was 4 out of the 5. And if we did the whole sample, in this case 5, we get exactly the mean. Okay, so what do you notice is happening with these? Not necessarily a trick question, but what do you notice is happening?
They're all averaging out to 80, or they're all coming back together.
So they're getting closer and closer to 80. So what term do we talk about in terms of spread? What's the thing that talks about spread? Nope, median's in the middle. Standard deviation. So as my sample size gets larger, my standard deviation gets smaller because they're more compressed. Okay? That's helpful. Because remember, standard deviation tells me if I get my standard deviation, I can tell how much is closer, like the percentages, right? I know within 1 standard deviation is about 68%, 2 is 95%. So it's like I can quickly, easily figure that out. It's like, okay, within 2 of these, so the smaller that standard deviation, the better my overall calculations are going to be, the lower my error is going to be in my information. All right. Questions with that? Okay. So we're going to go back to those numbers. All right. I want you to find me the average or the mean of those 10 numbers. So those were the means of 2, right? Of each of the samples, correct? So now find me the mean of those. Yes. Good. Wait a minute. Everybody else a shot. Why did you do it? Okay. Good. It was just a couple steps down the line. Did you already figure out the other one too? Figure out the ones before. Yeah, do the groups of 4 for me. Because I'll just ask you that one in a minute. I'll save the class the calculations. All right, what's the mean of all those? Huh?
80.7.
I check your calculation again. You missed the number. You typed the number in wrong somewhere. It's okay.
What was it supposed to be?
It should have been 80. All right. So that U symbol typically stands for mean, right? I have another symbol next to it, though. I have that little line with the X. Remember, that's the samples. Okay, so my sample mean for the first one was 77. So that would be the bar over the X. That's a sample mean. All right, the M stands for the mean of the whole data. That little thing, that bar over the X means the sample mean. But now I'm finding the mean of all my samples. And it's also 80. And I can't remember your name. Deidre. You did the force, and what was the mean of that? 80. So actually, and this is always true, the mean of all of the samples will be exactly what the mean of the population is. So if I found every possible sample and then did the mean of those, I would have the mean of the sample of the actual population. That's helpful. That's extremely helpful. Because that means when I'm doing my bell curve, I know the mean of the population and the mean of the sample mean is also right in the middle of my bell curve. Okay? And I can figure this out without having to do every possible sample, which is the goal. I don't want to have to do millions of different samples to figure this stuff out. I want to know that my mean is somewhere within this range. Okay? All right. So we were able to figure out the means. And we know that the higher the sample is, the more compressed it's going to be, which means the smaller my standard deviation is going to be. But now let's find my standard deviation. So we used a calculator to find standard deviation before, and we can kind of do it again. So we don't have to necessarily do this out. So I think I used calculator.net before. So, all right. So what we're going to do is we're going to find the standard deviation of those 10 numbers. So you should have those 10 numbers written down somewhere on your paper. And I'm just going to take a picture of this so I can type them in. Here. There. Now, this is going to be population because I have them all. Wait. Hold on. I think I typed the number in wrong. Yeah, right there. Okay, better. Much better. All right, so my standard deviation is 2.09. for this one. And 341. All right, so do the same thing for my 4 numbers. The sample size is of 4. So do the same thing for this one. Now, would I expect this one to be bigger or smaller than what I just got? Smaller, because it's more compressed, right? What did we get? 0.85. So the standard deviation for the first set, so in essence, the population standard deviation, was 341. The standard deviation for sample sizes of 2 was 2.09. For 3 was 1.39. For the 4, the one you found was 0.85, and then 5 would be 0 because there's no variation. So as my sample size gets larger, my standard deviation gets smaller, which makes sense. What does that mean for my error? As my sample sizes get larger, what would happen to my error? What would happen to how far off the mean I would actually be? Because that's really the error, right? I'm going to tell you the mean, and the error is how far off I'm going to be. So as my samples get larger, what should happen to that error? It should get smaller, right? Because my standard deviation is getting smaller, so my variation is getting smaller. So that means I have a higher percentage probability of being closer to that mean. Okay? So that's what the standard deviation is trying to show us here. Now, we don't want to have to sit there and do this out for every single problem because this would be annoying and we'd have to do a ton of work to do it. So there's got to be a better way to do this. There is. So here's my 2 formulas. To do any of this, you have to be given your population mean. Well, you have to be given some information about the mean, but you have to be given the population standard deviation. So your population mean will be the same as your sample means. Your standard deviation will be the standard deviation of the population divided by the square root of the number of your sample.
Listen.
All right. Let's do it. All right. So it says a report by the U.S. Census Bureau says the mean living space for a single family detached home is 1,742 square feet. Does everybody know what a single family detached home means? Basically means it's not attached to anything else. So townhomes, condos, and they actually have to say this because now a condo, I still to this day, I don't know how many times, I do not understand the purpose of a condo because in essence, you're buying an apartment. But they're houses and they're typically a lot smaller. So a single family detached home is a lot of what you'd see around here. Most of our houses over in this area are detached. So 1,742 square feet. And a standard deviation of 568 square feet. Okay. All right. So, based on what we know right now, before we go on and do the other things, one standard deviation would be what would be the range for one standard deviation? How would I find one standard deviation? The low value and the high value. Yes, I'm going to add 568 to that. I'm going to subtract 568 to that. And that would give me what percentage of all homes? Very good, 68%. Okay. All right. So we're going to take a sample of 25 homes. What's the mean and what's the standard deviation of that? Okay. Now, remember, we don't know which 25 homes. So what do we say about the mean? The mean is going to be what? It's going to be the same, right? So the mean for this is still 1742. What's the standard deviation for this, though? It's not the same. Otherwise, it would be no work at all, right? It's always what's given to you. You're good. But that also means that it doesn't matter the sample size. So we already know the sample size matters. So what was the formula for standard deviation? We take the standard deviation of the population and divide it by the square root of my sample size. So in this case, I'm taking 568 and dividing it by the square root of 25. So I got 113.6. Okay. So what does that mean? When we're looking at it, what that means is now if we look at, again, one standard deviation, right? We'll just keep doing with the one standard deviation, make things simpler. So if I added and subtracted the 113 from that, I would get 1628.4 to 1855.6. So if I was to randomly take a sample of 25 homes, I have a 68% chance that my mean of those 28 homes is between 1628 and 1855. Okay. So you've got to remember the goal of all of this is that in the end, I won't know that. Right? Because if I know that, I don't need to do any work. I have the mean. I'm good. All right. The goal is to be able to figure out to take a sample of information and be able to come up with a reasonable estimate of what that is. Okay. So if you wanted to figure out the average number of people that wear red or wear pink on Wednesday, okay, we can't ask everybody, but we can ask a random sample. And based on that random sample, I can figure out what the mean is. But I'm not going to get it exact. I'm going to get a range. All right. And that's what I'm looking for. Where would I fall? How close would I be? Okay. Now, if we did 500, do the same thing. So if we looked at B, the only difference, the mean's still going to stay the same in this problem, but now I'm divided by the square root of 500. Now I'm down to my standard deviation of 25.40. So remember, if I took 500 homes out of the entire United States, I would have a 68% chance of getting a number between 1716 and 1767. That's one standard deviation. Two standard deviations as well. Almost 95. So if I did another, I get 1691.2 to 1792.80. So I have a 95% chance that I'm going to get a mean between 1691 and 1792. And in this problem, I know my mean is actually 1742. So that's a pretty good estimation, right? That if I just chose 500 homes out of the entire United States, that I'd be within 50 of the actual mean of all of the houses in the United States. What if I did a sample size of 3,000. Okay. So we're within 10 square feet of the actual range, right? Or if we did two standard deviation, 20. How many single family houses do you think are in the United States? $82 million. Okay. But if I chose just 3,000 of them, I'm within 20 square feet. I have a 95% chance of being within 20 square feet of the actual value of all 82 million houses by choosing a random sample of 3,000. Okay. Here's an interesting thing, though. Does this problem, the calculations that we just did, do they have any connection necessarily to the houses? If this number right here, as that number keeps getting bigger, this number keeps getting smaller, right? This number doesn't matter what we're talking about. That number right there changes. If that number is smaller to start with, this number is going to get infinitesimally small. Okay. So if I was to look at anything, the calculations are the same. All right. So when you get up over 1,000 or so in your sample size, you're pretty darn close to the actual value. No matter how big, like this problem right here, I talked about, but 82 million showed up nowhere in this problem. Okay. If I was 300 million, it didn't actually change my statement I made a minute ago, where if you took a sample size of 3,000, you'd be within 20 square feet of the actual value. Okay. Now you can start to see how instead of having to ask 300 million people, I could ask a couple thousand people and get the answer. And it's because of this concept. It's because somebody went through and actually proved that this actually works. Okay. All right. Let's give you one more problem to do. I will let you guys go. Let's do this. Maybe this. I'm trying to find a good problem for you guys to try. Let's do this one. All right, try this. To be fair, that's a weird title of a paper. Our baby's normal. What's the population? Babies. Very good. We've learned. You didn't say like babies' weights or anything. Babies. That's the population. What's the variable? The weight. Good. And yeah, you might want to qualify and say in grams because we weigh things differently. One of these years, the United States will get over it and actually move to the metric system. One of these years. God. Everybody thought this was the last year we're going to have it. We're not. So people like, because last year, remember they voted everything up. They never passed the law that actually got rid of daylight savings. So we still have daylight savings. We're still switching back in November. And like,
Wasn't it for the wars?
it was originally to save power. They determined that during the waking hours, like when it was light, if the light was during when you were working actively up and everything else, you'd use less energy because you wouldn't have the lights and stuff on. So, but nowadays, even if we're in a building, we still have the lights on, even if it's sunlight outside. So it's not saving nearly as much energy as they would normally have thought. But yeah, that's actually what it had to do. Some people think it had to do with farmers, and farmers don't care what time of the day it is. When the rooster crows when the sun comes up, it doesn't matter if it's 4 o'clock or 8 o'clock. All right. So what's the mean for a sample size of 200? 3,369. Very good. What's the mean of the sample size of 400? 3,369, because that's what we're going with in this case. Very good. That'll change in a couple chapters from now, because I won't give you that anymore, and we'll have to figure things out. So, all right. So what's the standard deviation for a population of 200? So we did, I haven't actually done it, so I'm going to assume you're right. You did that divided by the square root of 200, and you got what? 41.08? That sounds reasonable. And then if we did a sample size of 400, and the mean stays the same, so I didn't write down necessarily the mean. So if we just looked at 400 babies, we're within 60 grams of the actual weight. And since we're Americans and we have no idea what 60 grams is, it's 2 ounces. So we're within a 95% chance to be within 2 ounces of the actual mean if we just took a sample of 400 babies. Okay. So you can see how small it really gets. Like it's like the sizes. Like you would think, oh, I'd have to look at if I asked you this in the beginning, you'd have to look at thousands of babies. It's like, oh yeah, there's no way we get that close. But with a very small amount of people, we can get really, really close to the actual values. All right, we're done for today. Finish up chapter 7 on Thursday. You too. Good.